Okay, chapter 13 is all about solutions. Okay, so not solutions to your problems or to problems of the world, but we mean chemical solutions, which are homogeneous mixtures of more than one component. And so we tend to talk about solutions like things that dissolve in water or perhaps an organic solvent, but really any homogeneous mixture is technically a solution to a chemist. So let's look at table 13.1, which gives examples of perhaps some surprising solutions. You can have a solution of solid in solid. So brass is a mixture of zinc and copper, and it is technically a solution because there are two different components and they are mixed down to the atomic level, so they are a homogeneous mixture. Solid and liquid, that's sugar water, that's easy enough. Liquid in solid, so mercury, which is a liquid at room temperature, can be mixed into silver, which is a solid at room temperature. And that's what dental amalgam is made of. That's not used so much anymore because of the danger of working with mercury and because of the aesthetics of having shiny metal bits in your teeth. I've got a few, but people these days tend to like white fillings instead of the silvery ones made from dental amalgam. But anyway, that was historically the way that teeth were filled, with a liquid in solid solution. Okay, liquid in liquid. Gasoline is a mixture of different hydrocarbons, so that is a solution. You can have a gas dissolved into a solid. So hydrogen gas will intercalate itself into solid platinum metal. Not just like coating the surface, but working itself into and amongst and between the platinum atoms and many other metals as well. In fact, if you are ever working with high vacuum research apparatus, you need to be careful that you don't have gases dissolved into all of the metal parts that you're using to build your experimental apparatus. Usually when you first pull a vacuum, you'll need to spend quite some time getting rid of gases that just begin leaching out of the metals. It's really bizarre. Gas and liquid, of course, carbonated soft drinks have carbon dioxide dissolved in them, and there's oxygen dissolved in the ocean. That's why fish are able to survive. And then gas in gas, and so perhaps the most ubiquitous and abundant solution around us is the atmosphere itself. Oxygen and nitrogen and other components are all mixed together at the atomic level, and they make up the atmosphere around us. So in a solution, you're going to have two categories. You'll have the solvent. And the solvent is really technically whatever you have the most of. So it is the majority component. You'll have solutes. Solutes. And solutes are any minority components. So you can have more than one solute, and they're anything that you have less than, they're anything that is a minority component. And so if we take salt and put it in water, for example, we're going to have a whole ton of water, and we've added a little bit of salt to it. So water is the solvent, the salt is the solute, and together they make the solution. And when we start to talk about different ways of measuring the concentration of solutions, we're going to have to be really careful to keep track of the difference between the solvent, the solute, and the solution itself, which is the combination of the two. Um, so I'll go ahead and erase this. Solubility is the ability of a solute to dissolve into a particular given solvent. And so you can talk about solubility in two ways. You can say just yes or no, like does salt dissolve in water? Yes, yes it does. Does plastic dissolve in water? At least say HDPE plastic that makes your milk jugs and things. No, it does not dissolve in water. So that's one way to talk about solubility. And then you can also get a little bit more refined and talk about, well, how much salt can dissolve in water? Can I pour an infinite amount of salt into 1 cup of water? No, eventually it'll stop dissolving. So we can also talk about solubility quantitatively using numbers. Now, in general, there is a rule that like dissolves like. And that's maybe a little bit of an archaic sort of language, but what we mean here is that in terms of the types of intermolecular forces that substances can exhibit, solute will dissolve in solvents that have intermolecular forces of the similar type and strength. So, for example, there are some solvents like water. This is a polar solvent. And so water is able to dissolve polar molecules. Very effectively. Something like sugar that has a lot of oxygen, hydrogen groups on it, and so a lot of fairly strong polar groups. It's able to dissolve hydrogen bonding solutes. That's actually what sugar really should belong in. That's why I thought of that and wrote it up there. Okay, so sugar is capable of hydrogen bonding, and so you can actually dissolve a surprising amount of sugar into water. And polar molecules, something like, say, let's think of a good one. A polar molecule that is not capable, of hydrogen bonding is going to be a lot less soluble in water, but it's still possible. So something like acetone will dissolve in water. And then also salts, some of them will be soluble because of ion-dipole interactions. And that's water being polar is able to provide half of that equation, ion-dipole. But water won't dissolve everything. Water won't dissolve oil. It won't dissolve wax. It won't dissolve gasoline. So there are a lot of things that water will not dissolve. Something like hexane. This is a non-polar solvent. And so it will dissolve non-polar molecules. Hexane is a really good solvent for things like oils and waxes, for things like hydrocarbons like octane, gasoline, kerosene. All of those things will dissolve wonderfully in hexane, but a lot of these will not. Salt will not dissolve in hexane. Alcohols will not dissolve in hexane, things like that. And in fact, if you recall to your 1215 lab, when we were investigating the reactivity of halogens, we took advantage of the different solubility properties of water and hexane in order to sort of separate out the halides like I minus, Br minus, and Cl minus from the halogens, things like I2, Br2, and Cl2. And you may recall that all of these non-polar molecules would dissolve preferentially in the hexane layer. So that's what we mean by like dissolves like. And in just a few minutes, we'll talk about the energetics of the solvation process, and it will kind of explain why this principle of like dissolve like applies in the first place. But let's look at the solvation process on a microscopic scale. And in particular, we're going to look at the solvation of an ionic solid. So here we have a diagram showing an ionic lattice. This could be something like sodium chloride, or it could be something else. And you see there's positive and negative ions, and they're actually held together very strongly by these ionic attractions. Well, a molecule that is in, where's my cursor? There we go. A molecule that is in the center here is surrounded on all sides by, so this anion is surrounded on all sides by cations that are going to hold it rigidly in place. And it's not going to be dissolved by water. However, an anion that is on the edge here, a corner in particular, well, it only has a small fraction as many attractive interactions with its neighbors. It is exposed to the water on the outside, and the water is going to surround it. And because water is polar and has a positive side over here by the hydrogens and the negative side over by the oxygen, it's going to surround it all with its positive sides facing that anion. And eventually it's going to kind of pull it away. And once you have this anion pulled away from the rest of the lattice, then it's going to diffuse out into the bulk of the liquid, and it is never coming back. And so that's how the solvation process starts. And once that anion is gone, well, then the next ion is exposed and ready to go. And so when an ionic solid dissolves, or really when any solid dissolves, the process will start on the outside with the parts that are exposed to the solvent, and it will work its way inward, and it does take some time. Likewise over here, if you have a cation, then the water molecules will surround it, but they'll just orient themselves oppositely so that the negative side is facing the cation and the positive side is facing outward. So here we have what we can call a hydration shell or a hydration sphere of water molecules around that cation. And the reality is there will be even more water molecules forming a second and a third, sometimes as many as 5 or so layers of water molecules, which will orient themselves in order to take advantage of these ion-dipole interactions and stabilize that cation in solution. So if we look at the energetics of this process, then 3 things will happen. First of all, the solute-solute attractions have to be broken. In the case of the ionic solid, that's the ionic attractions between the cations and the anions. Once those solute-solute attractions are broken, then the solute particle is going to go out into the bulk of the solvent, and that actually breaks up solvent-solvent attractions as well. The solvent attraction, the solvent has to make room for the solute, and so that's going to disrupt some solvent-solvent attractions. Those are both positive energy steps. It takes energy to break the solute particles apart. It takes energy to break the solvent particles apart and make room for the solute. But of course they are replaced by new interactions. solute-solvent interactions. And those new interactions will be negative energy. Any attractive interaction will lower the energy of the system. And the net result of this whole process, breaking the solute, the solvent, and then forming the new interactions, the net result of that process is going to be your enthalpy of solvation. And in this case, they show an enthalpy of solvation which is exothermic. That is, the new solute-solvent attractions are stronger than the sum of both solute-solute and solvent-solvent attractions. That's not necessarily always the case. And so you can have enthalpies of solution that are positive or enthalpies of solution that are negative. And we'll see some consequences of that in the next section. But they could be positive or negative. Now, for things that are entirely insoluble, then the energetics here are just not favorable. The solute-solvent attractions, let's clear this ink here. Okay, so let's suppose that your solute-solvent attractions are not very powerful, and you end up way up here. Then your enthalpy of solvation will be a massively endothermic process. And endothermic processes tend to not occur spontaneously in nature. Sometimes they do if they're driven by entropy strongly enough, but a hugely endothermic process is not something that you see spontaneously in nature. And so things that are insoluble are those things that have this kind of a schema where their enthalpy of solvation is just hugely endothermic. There are not very good solute-solvent interactions, and so they're going to have this positive enthalpy of solvation. So what sorts of solute-solvent attractions are small compared to the solvent-solvent or solute-solute attractions? This is where like dissolves like comes into play. If you have a solvent that's hydrogen bonding, then it's going to take a lot of energy to break up those hydrogen bonds and make room for the solute. If your solute is nonpolar and the best that it can offer is dispersion interactions, then it's going to have a modest negative solute-solvent attractions energy, and that's going to make it non-soluble. That's why non-polar solutes don't dissolve in polar solvents. It costs too much energy to make room for these solutes that offer nothing in return. And then if we look at something like a hydrogen bonding solute in a non-polar solvent, then it's just kind of the opposite. In that case, it would take too much energy to break up the solute, and it doesn't really gain anything by forming interactions with a solvent that only does dispersion forces. That's why something like water does not dissolve into something like hexane. So the energetics here can explain the like dissolves like rule. And then lastly, this enthalpy of this delta H SOL, it's the enthalpy of solution. Sometimes I will call it the enthalpy of solvation. Solution and solvation are just two different ways to say the same thing. And then if your solvent happens to be water, then we can also call it the hydration energy, or the enthalpy of hydration. Hydration being a fancy word for dissolving something with water. And that's it for section 13.1.